Okay, so good morning, everybody. Well, we're now live on YouTube as well, and today we are going to talk about uh, an algorithm that is at the state of the art. Specifically, we are going to have a different style of lesson. As you noticed, I have uploaded a paper on Classroom, and we are going through the paper together today for two reasons. One is I want to see um, what kind of questions arise from reading a paper like this, if there are any difficulties that you may encounter given the background that you now have in reinforcement learning. And the other part is I want to help you in learning how to uh, read a paper of this kind and to highlight the parts that are actually relevant for you. Um, okay. Beyond that, we're going to also skim through some other material that is available online regarding software actor critic, this algorithm that we're going to talk about. And we are going to look at one implementation again that is available online for this uh, algorithm. Note that um, this algorithm will be one of the algorithms that you will have to use or implement by yourself in the uh, projects. We're not going through all of them, but overall, we're going to cover the categories of algorithms that we are going to see. There will be other algorithms that we're not going to read together, but they will be either simplifications or small changes compared to, for example, soft actor critic. And we're going to uh, look at another paper next time, which is proximal policy optimization (PPO). Okay, so let's start. Close this. Okay, and I will increase the size of the uh, document so that it's readable for you as well. Okay, so this is a paper from Berkeley, and it's named Soft Actor Critic. So you know what an actor critic algorithm is. We'll see why it's soft, but the title already says something about it. It's an off-policy algorithm. So you know what an off-policy algorithm is, where they're using a maximum entropy deep reinforcement learning approach. So deep reinforcement learning, we said it's reinforcement learning with neural networks, maximum entropy. We'll see what it means. And they're also mentioning the fact that they're going to use a stochastic actor. So the policy is stochastic and it's not deterministic. So when you read a paper like this, generally a good way to start is looking at the abstract first, and then reading through the introduction and the conclusions to understand the overall approach, the overall idea, and just to have clear in mind what are the contributions of this paper. After that, you can go back to the technical section and go more in depth into that. So I have highlighted already some parts for you. Specifically here, the authors are mentioning the fact that model-free deep reinforcement learning has been demonstrated to be useful on challenging domains, both video games, also control tasks. But these methods suffer from two challenges, which are brittle convergence properties, and this is because we're mixing into reinforcement learning deep neural networks, and partially for the same reason, but also intrinsically from reinforcement learning, there is also this other challenge, which is very high sample complexity. Sample complexity means that the algorithms to converge and to learn require a lot of data, a lot of samples. And of course, this is a problem if you want to apply these algorithms in real-world domains. So in this paper, the authors proposed soft actor critic, which is, as we said as we read from the title, an off-policy actor critic deep reinforcement learning algorithm based on the maximum entropy framework, reinforcement learning framework. Specifically, they combine off-policy updates. So you know what off-policy updates are. So just to recall that it means that you have a behavior policy that is generating your data and a target policy that is the one that we're learning about. In this specific paper, of policy will, I mean, overall means the same thing, but more specifically means reusing past experience, because the policy, the behavior policy that generated those data is an old version of the policy that we're learning about. So we are reusing data from this behavior policy that was my policy some time ago, and now I'm learning about the new policy after several episodes. So I'm reusing data, and that's why it is still an off-policy algorithm. The overall idea doesn't change. We have still a target and behavior policy, but it's a slightly different perspective on it here. And as I mentioned, they use a stochastic actor critic formulation, and they claim the fact that their method achieves state-of-the-art performance on several continuous control benchmarks. Okay, so this is the overall idea. So we now have a clear vision of what this paper is going to talk about and what are the main features of this algorithm that is being proposed. So let's look now at the introductions, the point that I highlighted about it. So here they set some background to the reader for understanding why a different approach is required. Specifically, they talk about the sample complexity problem and the fact that the algorithms have the brittle convergence properties. So for the sample complexity side, they mentioned the fact that even relatively simple tasks can require millions of steps of data collection, especially when you're using neural networks with reinforcement learning algorithms. This becomes even more visible in the case where you have high-dimensional states and observations, and the fact that this also leads to brittle convergence properties, brittle with respect to hyperparameters, meaning that, for example, if you change parameters like the learning rate, the exploration constant, and so on and so forth, you might not get the results that you want as easily. So basically the basing of hyperparameters that is good for the algorithm to perform well on complex tasks is very small, and so you need to carefully tune your hyperparameters, otherwise you're not going to get the algorithm to converge. They go even more in depth on the fact that one reason for poor sample efficiency in deep reinforcement learning algorithm methods is the fact that they're learning typically on policy, so they do not reuse all data. And this requires basically the algorithm to collect new samples, new trajectory for every gradient step that they want to do. So for every update that they need to do. They also put here some references of algorithms that are on policy deep reinforcement learning like TRPO, PPO, A3C. So as I mentioned, next time we're going to read PPO, which is um, an improved version of TRPO. So reading this will let you understand TRPO, and A3C is not really any difficult compared to what we're reading today and next time. Um, here they mentioned the fact that off-policy algorithms aim to reuse past experience or any kind of experience that has been collected, as we know. And this is not typically feasible with standard policy gradient formulations. Then here they also discuss some related material, but we don't need to go through this. Um, so actually, when you read the paper, you should read everything, of course, but I'm highlighting here for you relevant parts. So now, after setting the stage for the reader, the authors also discuss what are the actual contributions of this paper. So they say we explore how to design an efficient and stable model-free deep reinforcement learning for continuous state and action space. So this deals with continuous and action, continuous states and action space. To this end, we draw on the maximum entropy framework, which augments the standard maximum reward reinforcement learning objective with an entropy maximization term. What does this mean? So, as we said from the first reinforcement learning class, the goal of the agent in a reinforcement learning problem is um, to maximize the sum of the rewards collected over time, discounted or undiscounted, depending on the formulation of the problem. Now, they are changing this problem with an additional term where not only they want to maximize the reward, but also they want to maximize the entropy simultaneously. So this is a different objective that they're optimizing, objective function. um, They also say, more importantly, the maximum entropy formulation provides a substantial improvement in exploration and robustness, um, because maximum entropy policies are robust in the face of model and estimation errors. So what does it mean, maximum entropy? It means that the policy is the least committed to specific action. So the uh, policy is trying to keep the entropy high, which means that if there are two possible routes, two possible ways to achieve the goal, then the policy is assigning equal probability to both actions. For example, if two actions lead to the to similar result as actually to a result which is as good as the other action, then the probability assigned to these two actions is the same. While in normal algorithms, the policy is committing to one specific action, and this, of course, can be bad for exploration reasons, but also if you have uh, some estimation errors, then you're committing to a wrong choice, while in this case, you're keeping your possibilities more open. So they say in this paper, we demonstrate that we can devise an off-policy maximum entropy actor critic algorithm, which we call soft actor critic, that provides both for both sample efficiency, learning, and stability. So they are actually, as you noticed here, they are actually now answering to the problems that they discussed at the beginning. They say deep reinforcement learning is unstable due to the small basing of convergence for the hyperparameters, and also it's very sample complexity is very high. So with this algorithm, we are trying to solve these problems exactly, And we're aiming for sample efficient learning and stability. Um, okay, let me see if there are some questions related to this introduction, but I think there should be straightforward. And as soon as you have questions, please post them so that we can um, cover them. I'll check every once in a while. Um, okay, so this is the introduction. As every paper, not only you need to present what is the problem that you are dealing with, but you also need to um, uh, rely on previous literature. And this is what is typically done in the related work section. So when you write a paper, you will have always a related work section. And in this related work section, you will discuss what is the previous literature related to your um, uh, related to what you're doing. Okay, so let's read what is written here. Our soft actor critic algorithm incorporates three key ingredients: an actor critic architecture with a separate policy and value function networks, and of policy formulation that enables reuse of previously collected data for efficiency, and entropy maximization to enable stability and exploration. So now for each of these three ingredients, they will go in depth on the related literature, on the related material, on the related work. So actor critic algorithms are typically derived starting from policy iteration. We know this because we have seen this in our course, which alternates between policy evaluation and policy improvement. So in policy evaluation, we assume the policy to be fixed and we evaluate the policy. In policy improvement, we use the value function to compute a better policy. Um, so they also mentioned the fact that in practical large-scale reinforcement learning problem, it's not possible to run each of these steps to convergence, and you typically optimize value function and policy in a joint way. So the policy is referred as the actor and the value function is the critic. Then they mention a bunch of actor critic uh, algorithms here that build on policy on policy gradient formulation to update the actor. Um, they recognize the fact that there has been already some effort to increase the sample efficiency while retaining robustness. And this has been done by trying to incorporate of policy learning in actor critic methods. Uh, However, of policy algorithms still uh, I mean, have some stability problems, especially specifically they refer to the deep deterministic policy gradient algorithm, DDPG, which is, as they mentioned, a particular popular of policy actor critic method. And it's a variant of the deterministic policy gradient using deep neural networks. So this algorithm uses the Q function estimator to enable off policy learning and a deterministic actor that maximizes the Q function. So already you can notice the difference here in the fact that the actor in DDPG is deterministic, while here there is a stochastic actor, and DDPG also preserves the standard reinforcement learning objective and does not add the maximum entropy component to it. So these are already two different differences between DDPG and SAC. Okay, so they continue by mentioning that unfortunately, the interplay between deterministic actor network and Q function typically makes DDPG extremely difficult to stabilize and brittle to hyperparameter settings. And actually, I can confirm that because I've been running few experiments with DDPG, and it's pretty hard to have it converging if you don't search for the correct hyperparameters. And as a result of this, it's difficult to extend DDPG to complex high-dimensional tasks. And compared to policy gradient methods that are more sample complex, however, these on-policy methods typically are more stable and produce best results in complex settings compared to algorithms like DDPG. So they say that their method combines off-policy actor training with the stochastic actor and adds the maximum entropy objective to the reinforcement learning one. So after discussing what are the related works in the actor critic land, they now go to discuss what is the literature on maximum entropy reinforcement learning, and they discuss what this means. So maximum entropy reinforcement learning optimizes policy to maximize both the expected return and the expected entropy of the policy. So this has been used in several contexts, specifically in inverse reinforcement learning, where the objective in inverse reinforcement learning is to look at some trajectories of some expert and to recover the reward function. So it's the inverse problem of reinforcement learning, where the direct problem is learning the policy from the reward function, and the inverse problem is given some trajectories sampled from the policy, from a certain policy that it's unknown to us, then we want to recover what is the reward function. And there are several reasons to do that, but we don't need to discuss this now. So they discuss the fact that there are algorithms like GPS, guided policy search, that uses the maximum entropy distribution. And there have been also other algorithms, more entropy, that used this approach more consistently. They also say that most of prior work in this context has assumed discrete action space while they're dealing with continuous action spaces. Okay. Which is one of the reasons, by the way, for which they use the actor as an approximate sampler, as we'll see in our reading. Okay. Let me go again to check whether there are questions, and it seems like there are no questions. Okay, so we are now starting the technical section of this paper, where the technical section means typically some preliminaries, background, if you don't, for the reader to get into the topic, then the actual algorithm and contribution, and finally the results and the experiments. So it's typically good to have in a paper a preliminary section where you introduce your notation and the frameworks that you're using. For example, the framework of the Markov decision processes and the maximum entropy reinforcement learning. So while in the previous section they discuss overall the idea and what are the approaches that use these kind of topics, these kind of frameworks, and contribute to similar algorithms, here they go in detail and explain what these frameworks are, and then what is the actual contribution of the paper. So they introduce the notation here, and the notation is the standard MDP notation, where they consider any infinite horizon Markov decision process, which is, as we know, defined as a tuple SA P, which we denoted as T and R, where the S is the state space, A is the action space, which is continuous, and also the state space is continuous in their setting. And then there is the transition function that it's a mapping from states and actions to states. And here it's written as a probability. So basically, it's the probability density of the next state, st plus 1, given the current state and action A. And they assume that the environment emits a bounded reward, meaning that it has a minimum and a maximum on each transition. Then they use the notation that we have seen basically when looking at policy gradient algorithms, where they use rho pi of S and rho pi of SA to denote the state and the state action marginals of the trajectory distribution induced by the policy. Okay, this is the notation which we are pretty familiar with. So this is the state distribution and nothing weird. The transition function, the reward function, state and action spaces are continuous. Okay, so now they set the background on maximum entropy reinforcement learning, and they basically say formally what they already said in the introduction in words, and what I already explained to you, which is the fact that standard reinforcement learning maximizes the expected sum of the rewards. So in expectation, where the states and the actions are sampled from the trajectory distribution generated by the policy, then this for this state and actions, we just sum the rewards, and in expectation, this is what we are maximizing. They consider a more general maximum entropy objective, which favors stochastic policies by augmenting the objective with the expected entropy of the policy over the state distribution. So the objective function that they are now trying to maximize is the following, where we have still the reward component, nothing has changed here, plus there is an alpha here, which is a temperature parameter that can be put to 0, and this basically, if this is put to 0, then we have the standard reinforcement learning objective that multiplies the entropy of the policy. Okay. So they mentioned the fact that conventional objective can be recovered in the limit as alpha goes to 0, and for the rest of this paper they will omit writing the temperature alpha explicitly. Why? Because if you divide everything by alpha, this means that you can just scale the rewards and not have this explicit alpha written over here. So they mentioned this by saying we will omit writing the temperature explicitly, as it can always be subsumed into the reward by scaling it by alpha elevated to the -1, so dividing by alpha. So they explain a bit better what we already discussed briefly before. This objective has a number of conceptual and practical advantages. First of all, the policy is incentivized to explore more widely, because it gives up on clearly unpromising avenues, but still at the same time, the policy can capture multiple modes of near optimal behavior. So the policy will commit with equal probability mass to those actions, which is what I described before. So this has been described in this background section for related to a finite horizon setup, because you notice here that there is no discount factor, but the same formulation can be easily extended to an infinite horizon problem by introducing the discount factor, which we already know. So now we can go to the actual contribution of this paper, but again, let me check for questions. Guys, if you have doubts, ask questions, because again, you're going to implement this stuff. If you, so hopefully you understand it well now. Um, so let me go, before continuing on the paper, let me go on this website, where they also have some additional material that is useful uh, to read. That basically it's sort of a summary of the paper, and it's also the website that is providing us with an implementation. So this is spinning up from OpenAI, where you will find basically all the reinforcement learning algorithms at the state of the art to be implemented. Now, I want to be clear on this. You can actually, you have to look at this implementation when you will implement your algorithm. But the idea is that you, after looking at this, you work by yourself and you try to understand it, and start from scratch without using this code, of course, because first of all, it's easy for me to check this, and second thing, you learn nothing if you just copy the code from here. So I want to read some more here on the entropy regularization. So a central feature of SAC is the entropy regularization. The policy is trained to maximize a trade-off between expected return and entropy, which is a measure of randomness in the policy. So the entropy will tell us how random the policy is. And this has a close connection to the exploration-exploitation trade-off occurs, because increasing the entropy results in more exploration, which can accelerate the learning later on. And it can also prevent the policy to prematurely converge to a bad local optimum. So the definition of the entropy is here. So we're going to look at this, given that this is not made explicit in the paper. So the entropy is a quantity which, roughly speaking, says how random a random variable is. So if a coin is weighted so that it's almost always coming up heads, then it has a low entropy. If it is evenly weighted and has half chance of either outcome, then it has a high entropy. So basically, this is telling us how deterministic a certain random variable is. So if there is one outcome which is very, very likely compared to all the other ones, then the entropy is low. Otherwise, the entropy is high. And then, so the formal definition for this is let X be a random variable with probability mass or density function P, then the entropy H of X is computed from its distribution P according to the following formula. So in expectation, so you are sampling from this distribution, and this is equal to the minus logarithm of this P of X. Okay. And then here there is nothing else that is being added compared to what we have read in the paper already. Okay. So let's go to the actual contribution of this paper. Okay, our off-policy soft critic algorithm can be derived starting from a maximum entropy variant of the policy iteration method. So they start from policy iteration, which is where we started from as well. Then they add this maximum entropy component, and then they derive from the policy iteration with this maximum entropy component what is the soft policy iteration. So they I think they mentioned this here, but I cannot find it now. Okay, yes. So they start in a tabular setting to enable theoretical analysis and convergence guarantees. That's why they call this part soft policy iteration, because they're using basically no function approximator, and they're using a tabular setting. And so this is very close to an actual policy iteration algorithm that alternates between policy evaluation and policy improvement. So in the policy evaluation step of soft policy iteration, we wish to compute the value of a certain policy pi, standard thing, according, however, to the maximum entropy objective in equation 1. Remember that equation 1 is the following. So the objective is the sum of the rewards plus the entropy. So for a fixed policy, the soft Q value, so the Q value, which is the standard definition of the Q value, becomes soft because it adds this maximum entropy component, can be evaluated in an iterative way, starting from any Q function. As usual, you can initialize your Q function as you want, and then repeatedly applying a modified Bellman backup operator, which is the following. So reward plus gamma that multiplies. So this is the recursive definition. Basically multiplies the value of the next state. But and this is here. There is nothing new basically except how V is defined, right? Because this is what we have seen in any standard algorithm: reward plus gamma that multiplies the value of the next state in expectation, of course, on the what are the possible next states that are returned by the transition function. But V in this case is computed as the Q function, so the expectation of the Q function. So we know that V is basically a weighted average of the Q function, where this weight is the probability of every action. So there is nothing new here, except that now we're adding this minus logarithm of pi, which is the definition. Right, so if we go here, this is the definition of the entropy. So our distribution is the policy, pi becomes P. So the logarithm of pi is what we are using in this soft policy evaluation step. So again, till here there is nothing new except that there is this entropy component which is added. So this is the soft state value function. So the first lemma that they introduced then is that consider the soft Bellman backup operator T pi in equation 2 and a mapping Q0, any mapping Q0 from state and actions to a real value, with the dimensionality of the action space being finite. And if we define the Q function at the next iteration to be computed as this Bellman operator that multiplies the previous Q function, then the sequence of these Qs will converge to the soft Q value of the policy. Then there is the proof that is in the appendix, but we're not going through the proof. So in the policy improvement step, we update the policy then towards the exponential of this new Q function. And again, this is nothing strange because we have seen that policies are often defined as the exponential of the Q function, so which is used as a preference function. Since in practice we prefer policies that are tractable, we will additionally restrict the policy to some set of policy pi, where pi here includes a group of a category of policy distributions, which can correspond, for example, to a parameterized family of distributions such as Gaussians. So they will say we restrict the space of policies that are interesting for us to Gaussian policies. And to account for this constraint, then we have to do a projection step, a projection of the improved policy into the desired set of policies. So on the one hand, there is the exponential of Q pi. Then we want, however, a policy which is a Gaussian. So we need to project this exponential of Q pi, or actually, project this exponential of Q pi into the space that we want, which is the space of Gaussian policies. In principle, they say we could use any projection, but it turns out to be convenient to use the information projection defined in terms of the KL divergence, Kullback-Leibler divergence, which is the following one. So basically, the KL divergence is telling you how different two distributions are. So basically, if you minimize the KL divergence, you're minimizing the difference between two distributions. And that's why, on the one hand, they have this exponential of the Q function, which is what you ideally want. On the other hand, you have this Gaussian policy, and you're trying to minimize the difference between these two policies in such a way that there is not so big difference, but still the policy that we are looking at is a Gaussian policy. I hope this concept is clear. If not, please ask questions related to this. And so that's why the new policy will be the argmin of the policies that belong to the Gaussian policy space of the KL divergence between this Gaussian policy and the exponential of the Q function divided by z pi old. So z is nothing else than a partition function that normalizes the distribution. And while this is intractable in general, so we cannot compute that, given that it does not contribute to the gradient y, because this is just a constant. So the gradient with respect to the new policy is independent to this, then we can ignore that term. So they now introduce the second lemma, which is the soft policy improvement lemma. Before we had the soft policy evaluation lemma that says let a pi old that belongs to the set of Gaussian policies and let pi nu be the optimizer of the minimization problem defined in equation 4. So this is equation 4. Then Q, the value of the new policy, is higher than the value of the old policy. So basically, this is the policy improvement theorem that still holds. There is a proof here, but nothing has changed basically the real idea from what we have seen in class. It doesn't change. So you can, of course, look at the details in the appendix if you're interested into that, but the important is that you understand the overall idea, because the concepts are exactly the same that we have seen in class. Okay. So now they release this fact that this algorithm will probably find the optimal solution, and we can perform it in its exact form only in the tabular case. So in the next section, we will formulate the algorithm for continuous domains, where we rely, of course, if we're doing tabular case, then this cannot be done in a continuous domain. So they extend their work with a proximate algorithm for continuous domain, where we need to rely on a functional approximator to represent the Q values, and running the two steps until convergence would be computationally too expensive. So the approximation gives rise to a new practical algorithm that is called soft actor critic. So switching from soft policy iteration to soft actor critic is required to deal with action spaces that are continuous and to use a function approximator. So now you cannot train until convergence everything, and that's why you have this soft actor critic algorithm. Okay, so questions, let's check. There are no questions. Yes, everything is crystal clear. Okay, anyway, so for the soft actor critic algorithm, they use a parameterized state value function, a soft Q function, and a tractable policy pi. These are three parameterized functions, three neural networks that are parameterized to parameters psi, theta, and phi. So for example, the value functions can be modeled as a neural network and the policy is a Gaussian with mean and covariance that are given by the neural network, which is exactly what we have seen also last time in class. So let me say a few more words about this. So there are different variants of this soft actor critic algorithm. Here, the one that is presented in this paper is an older version. There is also another version where the um, value function is not directly learned, because the value function can be computed, as you notice from here, directly from the q and the logarithm of the policy. So uh, there is no reason to train another neural network except for stability reasons. So you will find implementations that do not train the value function as well. More than that, they mentioned the fact that there is one Q function here. You will see later in the paper, also in other implementations, that are implementations that use one Q function, and other implementations that use two Q functions, where they basically do what we have seen in double Q learning. So they use the minimum of the Q values to compute the target for the update, in order to reduce the positive bias that might come up from it. But anyway, so the overall idea doesn't change. So we have in this specific version a state value function, a Q function, and a tractable policy pi, which are parameterized as neural networks. And specifically, the policy is parameterized as a neural network which predicts mean and covariance of a Gaussian. So the state value function approximates the soft value. So there is no need in principle, as I was mentioning, there is no need in principle to include a separate function approximator for the state value, since it's related to the Q function and the policy according to equation 3. So the soft value is trained to minimize the squared residual error between this, which is the definition of the value function, right? Equation 3. And what is actually being the current prediction from the neural network. So this is an L2 loss, right? A mean square error loss, uh, 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 where you are minimizing the distance between the actual prediction and the target, which is in this case the Q of the state and the action uh, minus the logarithm of the policy. So there are few things to notice here. So this soft actor critic reuses experience, meaning that when generating data, this data is not used to train immediately, but it's stored in a buffer, which is called an experience replay. And then for training, data is sampled from this buffer. And this basically means that you might be using old data, right? This is why the algorithm then is an off-policy algorithm. So you might be using old data that come from many versions before of the policy. So in computing this value function here, in computing this loss, you have to notice that the state for which we are computing the value is sampled from this experience replay, which is noticed here as the data set, while the action is being sampled from the current version of the policy. Okay. So this is, again, one reason for which this is actually working, because we want to correct and take into account the current policy while using old data, and this is how this is being done. The data, the state is sampled from the experience replay, while the action is sampled from the actual from the actual policy for the computation of the value function. So as they mentioned here, so D is the distribution of previously sampled states and actions of a replay buffer. So of this distribution of previously sampled states and actions, we are only using the state here. So this is the formulation of the gradient of this equation. This is basically computed automatically if you're using a framework like TensorFlow or PyTorch. Yeah, and they mentioned also here the actions are sampled according to the current policy instead of the replay buffer. So this is for the value function, for the state value function. Now let's look at how we update the Q function. And again, notice that this is exactly what I mentioned last time. What we have for training a value function, a state value function, or an action value function doesn't change from the general formula that I gave you last time when you're using a function of proximity. So this is nothing else than a mean-square error between the current prediction and a target, where the target, in this case, for the value function is equation 3. The target is computed according to this equation. Very simple. So there is nothing crazy here. So for the Q function, the soft Q function parameters can be trained to minimize the soft Bellman residual, where this is the mean square error of the current prediction minus the target, where the target is nothing else than the reward plus gamma that multiplies the value computed from the our value function neural network, state value function neural network. So let's look very carefully again at where we are sampling the data now. So for this update of the Q function, we are using completely old data because we're using the state and action that come from the dataset, from the experience replay. Okay. So that's why this is actually reusing data. Okay. So the update makes use of a target value neural network where psi can be exponential moving average of the network weights. I mean, this is another thing that can be done. So finally, the update of the policy, which might resemble the most difficult part, but it's actually not so difficult because so we can directly minimize the expected KL divergence. So you looking at this formula, you're saying, okay, but how the hell do we do this in practice? So in practice, the KL divergence formula is used as is. So it's the following one, with the exception of the fact that to have the policy being projected into this Gaussian space, they as you know, they emit from the neural network the mean and the Gaussian, but then this has a problem because you want to differentiate through your policy, and if you have a sampling step from this mean and Gaussian, then you have a problem because you cannot anymore. Basically, sampling is not gradients do not go through the sampling process. There is no way to have backpropagation going through the sampling. So there is a trick that they use, which is the reparameterization trick, where basically they sample these epsilon from a spherical Gaussian. A spherical Gaussian is a Gaussian centered in 0 and with standard deviation 1, and then they scale it down. So let's look at this from here, which is this is explained very well. So yeah, this is the value that you're sampling from this spherical Gaussian centered in 0 and with standard deviation 1, and then you're multiplying this value that you sampled basically you are scaling it by the standard deviation, and you're shifting it with the mean value. So this is very simple, and again, the idea is that this is the only way to have the possibility of having gradients flowing through the mean and the standard deviation, because the sampling procedure uh, is not differentiable, and you don't care of having your gradients flowing through this part, but you want your gradients flowing through the mean and the standard deviation. And so you sample, and then you multiply the sampled value through this, and this allows you to have gradients flowing. Okay, then the cost function is nothing else than um, this uh, this that we have written here, which is the KL divergence, which is computed as the logarithm of the policy, where the action is computed from the neural network with the sampling that we have just seen in the state that is sampled from the experience replay. And this is minus the Q of the ST, where the state is again the state sample from the experience replay, and the action is the action computed by the policy. So this is computed log probability density of the action that is computed by the policy. Okay. What else do we need to say regarding this? How do we get to this? Basically, if you put everything in the logarithm, this is how you get to this formula, right? Because you get rid of the exponential, this becomes logarithm of pi, and of course this becomes a subtraction. So they mention here that their algorithm makes use of 2Q functions to mitigate the positive bias in the policy improvement step that is known to degrade the performance of the value-based methods. So in particular, they parameterize 2Q functions with parameters theta and train them independently to optimize the cost function, this cost function that we have seen here, sorry, equation 7. And then use the minimum of the Q values for the value gradient in equation 6. So for this over here, and for the policy gradient here. Okay, so this is the overall algorithm. So if you have cleared this, then we can go to the experiments. But again, let's check questions first. And again, guys, I cannot believe that there are no questions, because I don't know, it seems quite hard to not have questions on new material like this. I would have questions if I was looking at this the first time. So again, if you have questions, I'll wait a couple of minutes before going to the experiments, the experiment section, so that I can give you time to think on questions. Okay, no questions are coming. So we'll move on to the experiment section. So the claims that the authors do at the beginning of the paper in the introduction is that this algorithm is more sample efficient and more stable. So the experiments that they do are actually in the direction of showing these characteristics. So to understand how the sample complexity and stability of our method compares with prior of policy and non-policy deep reinforcement learning algorithms, we compare our method to prior techniques on a range of challenging continuous control tasks from the OpenAI GYM benchmark suite. So OpenAI GYM is, you have already seen that. So as you see, this is stuff that is used in standard state-of-the-art reinforcement learning algorithms. So the stability of the algorithm also plays a large role in the performance. They say as easier tasks make it more practical to tune hyperparameters. But if you take the other algorithms that you think are more unstable and you bring them in more complex domains, then the already narrow basins of effective hyperparameters becomes even smaller. And so it becomes prohibitive, basically, to tune the algorithm to work well on this benchmark, leading to poor performance. So that's why they select these complex continuous domains where they aim at showing the fact that their algorithm is more stable independently of the hyperparameter, and also that they converge faster. So the sample complexity being smaller means that they converge faster compared to other algorithms. So they compare their method to DDPG, um, which is again an off-policy version of deep reinforcement learning methods, PPO, which is on policy. It's a non-policy policy gradient method, and soft Q learning, which is another version of policy algorithm for learning with maximum entropy policies. So they do this evaluation on environments which are Hopper, Walker, Alpha Cheetah, Humanoid, and Ant, where basically these simulated agents have to learn to walk or to move forward more generally. Um, and figure 1, which is the one that we're looking at, shows the total average return of the evaluation rollouts during training for DDPG, PPO, and TD3, which is another algorithm that they compare against. So they train 5 instances of each algorithm with different random seeds. So why different random seeds? Because the random seeds control the randomicity of your how you're sampling random numbers. So you want to make sure that you're not just being lucky with a certain random seed, and that's why you change random seeds to make sure that you're not just lucky for that seed. So, and then they mention evaluation rollouts, and these evaluation rollouts are computed every 1,000 environment steps. Okay, so um, so this is the average return. As you see, we're talking about million steps, right? So they stop the training after 1 million step. And you can see, so the SAC is the orange curve, PPO is the on-policy algorithm is the brown curve, and DDPG is the green curve. As you see, DDPG doesn't perform as well on the average return for most of these environments. PPO um, achieves performance that are comparable to soft actor critic, but typically soft actor critic converges much faster. So for example, in this case, SAC converges much faster. In this humanoid task, which is the most complex of the environment, it converges much faster. And again, PPO is capable of reaching the same performance, but not here, first of all, and second, with higher sample complexity. In several tasks, is not even able to compare with soft actor critic. Yeah, so SAC also learns considerably faster than PPO as a consequence of the large batch sizes. PPO needs to learn stably in a stable way on more high dimensional and complex tasks. They also do an ablation study where they compare stochastic versus deterministic policy to compare how the stochasticity of the policy and the entropy maximization affects the performance. So ablation study means how every element of this algorithm contributes to the overall performance. So to compare how the stochasticity of the policy and the entropy maximization affects the performance, we compare to deterministic variant of SAC that does not maximize the entropy and that closely resembles DDPG, with the exception of having two Q functions. So this is basically DDPG with two Q functions. And this is shown here. So deterministic, sorry, this is in the evaluation part. Yeah, figure 2. Okay, sorry. Okay, yeah. So here they're comparing the deterministic policy, which is the red one, over different runs, and the solid line is the mean, compared to a stochastic policy, which is the following. As you see, the stochasticity stabilizes training because the variability of the red lines is much higher compared to the variability of the blue lines, as you see. So the performance is comparable, and there is not as much um, instability during training. So then in the policy evaluation, since SAC converges to stochastic policies, then it is often beneficial to make the final policy deterministic. As you know, we also say this, when you do policy evaluation, you don't want to be stochastic anymore, you want to be deterministic. So for the evaluation, they approximate the maximum posterior action by choosing the mean of the policy distribution. So they compare basically this approach to the evaluation, so using the mean, to stochastic evaluation, where you're using still a stochastic policy, and of course the deterministic evaluation performs better. And then there are some other ablation studies that they did that you can look. I mean, you can look at them by yourself. They're not so interesting for us at the moment. So this is the paper. And this is really an algorithm that is used again at the state of it's an algorithm at the state of the art is used on several complex domains. And I mean, if you understand this algorithm, then you can understand several algorithms that are that you can find on scientific papers that have been published recently. Again, I don't see questions, so I'm going to move to look at the implementation just for one specific part. But I mean, for again, if you have questions, please look. Please don't wait to ask them. Okay. So this is the implementation from OpenAI. Again, this is spinning up, where they have this class for the experience replay. So the experience replay is this buffer where they are storing data and they are sampling batches. Right? This is just by sampling data. Really, nothing difficult comes from here. And then the soft actor critic algorithm has some parameters like batch size, alpha, so on and so forth. But let's look at the parts that we're interested in. So it uses this replay buffer, and then let's look at how they compute the Q function loss. So the Q function loss is computed by taking the data from the experience replay, where they're taking the observation, the action, the reward, the termination, and the next observation, the next state. So they compute the Q value of the observation and the action according to the first Q function, Q1 and Q2, and then they use you will see they will use the minimum. So after doing this, right, they this is the PyTorch version. So I'm looking at the PyTorch version now. So they post the gradient computation, because when computing the target, we don't want to uh, change. Basically, we don't want the gradients flow through the target, but only through the other part of the equation where we are computing the difference, the mean square error. So from the target, they're using the target Q values Q1, target Q values Q2, where the action 2 is sampled from the policy, and the target is computed on next state and next action computed from the policy. Uh, and then they compute the minimum of Q1 and Q2 target, and then they compute the target as reward plus gamma, that multiplies 1 minus termination times the minimum of this two Q function minus alpha, that multiplies the logarithm of the policy of the action in that state. Then the loss for these two Q functions is nothing else than Q1 minus the target and Q2 minus the target. So notice that the target is computed for both Q functions the same way. And this is the mean of the squared error that is then computed. So the final loss is the sum of loss Q1 and loss Q2. Note that this is under torch no grad, which again means that we are posing the gradient. So every time we compute the target, we want to pose the gradients, otherwise things get broken. We only want the gradients to flow through this and this. So the prediction in the current state and the current action, not in the target computation. So this is how they compute the loss for Q, which is exactly what was described in the paper. So again, reward plus gamma uh, that multiplies 1 minus termination, that multiplies. In the paper, they use the value function. In this implementation, they directly use the equation expanded, so Q minus alpha that multiplies the logarithm of the policy. So for the loss of the policy, again, they what they do is computing the Q1 pi, Q2 pi, then selecting the minimum, and the loss of the policy is very simply alpha that multiplies the logarithm of the policy minus Q pi, which is what we have seen in the paper, right? So if you look at the question, we compute the loss as the logarithm of the policy minus Q. Okay, so in the update, they initialize the optimizer to have basically to have zero gradient. They compute the loss for Q by calling the function that we have seen before. Then they apply the gradients. So backward is to apply the gradients, and then to compute the gradients, and then they apply the gradient through the optimizer using this step function in the optimizer. Okay, and similarly, they do the same for the policy, given the data that come from the experience replay. Very simply, and I mean, then there is this other part that is regarding the update of the target network, because there is a target network that, as I explained to you for deep Q learning, is used to stabilize the training. Then when to train, basically they are collecting samples from the environment and storing them in the experience replay, and every once in a while they update everything using the update function over here. So the algorithm is very simple in practice. As you see, it's one experience replay, two functions for updating, one function that calls the actual optimization functions of PyTorch, and one function that collects data and every once in a while calls the update function. Very simple. Again, you can find this implementation spinning up online. I mean, again, if you don't have questions, I will not spend more time on this. But and if so, basically the class is finished. But again, I would like you to ask some questions if you have, uh, possibly. So let me pause it here. I will wait 5 minutes. As usual, if you have questions, post them. I'll answer. Otherwise, okay. So, I mean, mm, I see no questions coming, so it's probably useless to continue waiting. So let me stop sharing